Hello, everyone. I'm Yanqi from Harbin Institute of Technology, Shenzhen. It's my honor to present our work in OSDI, fast and synchronous crash consistency with metadata write-once file system. Crash consistency is a fundamental requirement for file systems. It ensures that the correct crash recovery for data applications, such as database and storage for large language model, and so on. Recently, low-latency persistent memory, or PM, encourages file systems to pursue synchronous crash consistency. Compared to block-based file systems that use asynchronous crash consistency to delay persistence to improve performance, PM file systems ensures that every operation is persistent after its return. Such synchronous crash consistency brings two advantages. The first is that it can avoid a synchronization bug like misused fsync. The second is that it can avoid synchronization overhead by removing frequent fsync calls, as every operation is now persistent. As a result, numerous PM file systems adopt synchronous crash consistency to benefit its advantages, such as SquirrelFS and OdinFS. These file systems use two traditional methodologies for synchronous crash consistency. For a write operation, the first type tries to use additional writes to back up metadata first. Generally, file system is a representative one. It first writes data block, and then writes transaction to a reserved general area to back up metadata, and commits the transaction, and finally writes the metadata to its original place. Committed transaction is then replayed for recovery. However, this approach introduces double metadata writes. So, the second type tries to simply order I/O without extra writes. Log-structured file system is a representative one. It first writes data block, and then a log entry, and finally update tail in inode for commit. So, in this way, partially written metadata will never be visible in log-structured file system. These traditional approaches are well optimized for traditional block-based file system, but how do they perform atop PM? To answer this question, we study PMFS as generally file system, or JEFs, and NOVA as log-structured file system, or LFS. We break down their performance under a simple sequential 4 kilobyte write workload. And the results suggest that the synchronous crash consistency overhead atop PM can incur more than 75% overhead in the total I/O path. This significant overhead, as a result, leading to more than 15% PM bandwidth waste, suggesting that existing synchronous crash consistency approach do not suit well for PM. So why existing crash consistency has such high overhead under the synchronous context? Our findings show that the root cause is due to existing crash consistency methodologies incurs many small, random, and ordered metadata I/O. First, whether log entry writes, transaction writes, or inode updates, they are small and distributed across PM. This can cause great I/O amplification due to PM's coarse I/O granularity. Second, all the metadata I/O is ordered for consistency. They need to wait for previous data transfer, and thus limiting the I/O concurrency. And finally, existing crash consistency approaches incur many I/O across many different metadata objects, which further amplifies I/O overhead. To address this issue, our main goal is that to design a new crash consistency mechanism to minimize metadata I/O and ordering points. So, our key insight is that existing crash consistency approaches struggle to orchestrate I/O over many traditional metadata objects, such as inode, dentry, and so on. This compromise, however, mismatches with the goal to minimize metadata I/O. To address this, we resync metadata for the optimal crash consistency. Our intuition idea is that why not design one metadata package for each file system operation? And in this way, this one package for one operation design conducts only one metadata I/O for a single file system operation. And thus, we can minimize the metadata I/O. Let's see an intuitive file create example. For create operation, we first generate a metadata package containing both file name and inode information and other information for this operation. Then, we simply persist this package to the PM to indicate that this create operation is persisted. Further, we parse and manage this package to construct a file abstraction. And finally, the create operation is returned to user space for completion. We call this file system module as metadata write once file system, or WOFS. In this talk, we focus on how does WOFS persist and manage packages. So, for package persistence, the first question is where to persist a package. To decide this, our rationale is that log-structured I/O is not a must for PM, as PM is byte addressable, and it has faster random I/O performance than traditional SSD or HDD. Without log-structured I/O, heavy and complex garbage collection process can be also avoided. Thus, we propose a non-log layout. In this layout, packages are dynamically allocated and freed across PM using per-conf-free lists, similar to memory allocate and memory free. After we decide where to persist, we next need to persist the package. The problem here is that the package can be large. For example, a create package is 256 bytes, while the atomic granularity of CPU is 8 bytes. Thus, the package might be partially written if system failure occurs. So, to address this question, WOFS introduces to use checksum to protect the create package. As a result, the package can be written with the checksum with a single I/O command. And we verify its integrity by recalculating checksum and comparing it with the stored one during failure recovery. We now introduce the package management. The first question is that how to provide compatible file system services as package violates the traditional metadata layout. While traditional metadata objects, such as inode table, are fixed in the storage, it is easy to locate and parse them. However, given a create package, which can be placed anywhere, how to locate and parse it as a file remains a problem. So our approach is simple. We leverage an intermediate package translation layer to convert packages in PM into compatible metadata objects in DRAM to provide compatible and efficient file system services. For example, this layer converts the create packages as inode information and the directory entry structure. And we further organize them as inode table and file system name hierarchy. For write packages for the write operations, they are parsed as data block pointers and further organized as data block index for logical file data access. The next question is that how to reclaim the invalidated package. For example, an unlink operation for a remove operation can invalidate the create file and also its create packages. To reclaim the package, WOFS introduces an immediate package reclamation approach. It first reasons the causal dependency of operations in the critical path. For example, WOFS can identify that the unlinked package can invalidate a create package. Afterwards, WOFS reclaims the create package by simply returning its space to the allocator, which is similar to call memory free. So with efficient package persistence and management methodologies, WOFS can be practical and efficient. We now present WOFS evaluation. We implement WOFS within Linux kernel, and we evaluate atop OptDC PMM. We compare WOFS with a number of state-of-the-art PM file systems, such as SplitFS. We first evaluate the basic I/O performance. The experiment conducts FIO with 1 GB total I/O size with varied per I/O size. The results indicate that WOFS can consistently outperform competitors under any I/O size, thanks to its metadata write once scheme that minimizes metadata I/O overhead. More importantly, this minimized metadata I/O allows WOFS to reach PM bandwidth limits. We next study the performance on the varied total I/O size and fixed 4 kilobytes per I/O size. The results are similar. WOFS outperforms competitors by more than 15% and is very close to upper bandwidth limits of PM. More importantly, due to minimized package I/O and efficient package management, WOFS shows a rather stable write performance trend with the increased total I/O size, while SplitFS and Nova suffer degraded performance due to in-kernel metadata and GC overheads. We next measure the metadata operation performance among these file systems. We set up FXMark with 5 single-threaded workloads, including data operation, directory traverse, file creation and deletion, and file rename. The performance trend is similar. WOFS always shows the highest throughput. While under the directory traverse workload, WOFS, Nova, and PMFS show similar high throughput, as they are kernel file systems with well-designed VFS de-entry cache. We also show that synchronous crash consistency can even outperform asynchronous crash consistency. We here use a simple FIO sequential 4 kilobyte write workload with no fsync issued. We compare WOFS with Hunter and SuperFS. The later two file systems delay metadata I/O to the background to hide the metadata I/O overheads in the critical path. The results show that WOFS still outperforms Hunter and SuperFS, as these file systems will periodically flush metadata, which affects their foreground I/O performance. For other performance results, please refer to our paper. Finally, we draw a conclusion. Our work reveals that many small random and ordered metadata I/O can be the bottleneck for PM file systems with synchronous crash consistency. We introduce WOFS file system module to minimize metadata I/O overhead by designing a specific package as one metadata for a single file system operation. And thus we can achieve optimal one I/O and ordering point for metadata. Finally, we introduce a range of techniques to manage packages practically and efficiently. And our results show that WOFS can outperform state-of-the-art PM file systems and reach upper PM bandwidth limits. Thanks, and any question?